Hi, everyone. I'm here today with Carl from Divimath. We're going to have a bit of a conversation around the HDZero technology and hopefully ask and answer some of those questions that maybe you had about the technology, but also maybe some questions that you didn't know you had. And hopefully you'll find this interesting. So I'm going to launch right into it now. Thank you so much, Carl, for joining me for this call. I'm sure that everybody out there is going to be super interested to hear everything you have to say about HDZero and the technology that you have, because it's really impressive. So before we jump into the technology itself, can I ask a little bit about your personal background? You know, where were you born? Where did you grow up? Where did you study? And how did you come to be where you are today?
All right, thank you, Chris. I was born in China in 1972, so I'm almost 50 years old. So I get my all education, PhD from China, and in 2001. And in 2001, after graduation, I went to Silicon Valley for a job and stayed there for 20 years. So all my career is based on communication and video processing. My first job is ESS technology. I was doing the modem, right? Internet, the modem. Yeah. The young guy doesn't know that, but the older generation know the modem. What's a modem? Yes. After that, I was doing the video decoder, like the CVBS, exactly it's still using in our IPV. Is a dominant of today. Now I was doing the DVB-T demodulator, which is the digital video terrestrial for European. That's DVB-T. After that, I joined the Inteview, and I started a company in 2005. Then the company was acquired by TechWell. The TechWell is kind of very interesting. The TechWell that I designed the chip is called TWAA36. The chip is using inside the goggle for driving the OLED display.
Right.
That's right. That's very interesting. I don't know that until I get into LPV industry. In 2018. That's about 10 years later after I designed that chip. So in 2014, I started a company in the United States, right? And have the branches in China. So in Xi'an and Shenzhen, the R&D and manufacturers in Xi'an and Shenzhen. But the company, Divimath Inc. is a California-based company in Fremont, the same city as Tesla residence. Yeah. So that's the background of myself.
Fantastic. Oh, thank you so much, Carl. It's really interesting. It sounds like you've just got an enormous wealth of experience in this sort of area in the field of video and digital communication. So that's wonderful to hear about. Can you tell me a little bit more about the background of the company, Divimath? So you said you founded it and it's based in Fremont, California. But obviously you yourself and the company have strong links for manufacturing and things of that nature, I guess, in China. Is that right?
That's right. So the company, yeah. So because I'm Chinese, and most of the manufacture of the PV, I think, is based on China. Mm-hmm. So Divimath will do the same. But I was not going to do the VTX, VRX, those kind of things. I was only, we call it IC, Fabulous IC Design Company. Our product is a chip. Everybody uses our chip to build up like the goggle, right? Build up the VTX, VRX. That's my initial target. It's still my target, but HDZero is kind of very new. Nobody will going to risk themselves because of new technology. And also because another digital solution is so strong, so nobody want to compete with them. So I have no choice but to design the VTX and the VRX myself. So I don't have choice to do that. If I do have the choice, I will do what I'm good at. That's design and selling a chip.
Right. So that's really your core expertise is in, I guess, ASIC design. Is that right? Application-specific integrated circuit design.
Exactly. I always talk to people. I'm not more than a qualified ASIC designer. That's me.
Fantastic. And I think for those people maybe who aren't aware, the application of digital video in FPV really does require specific silicon, like specific integrated circuit design, because our requirements are so extreme in terms of like latency and throughput and that sort of thing. So yeah, that skill set's obviously super valuable in this field. And so you say you started off as a fabless semiconductor company, and certainly I also work for a fabless semiconductor company as well, based here in Cambridge. So I know all about that. So how did you come to sort of transition from that into products?
Right, it's kind of very weird. So when I'm doing the low latency video link, it's not for APV. I don't know APV at all. So I was back to 2015. So I bought a gear, it's a HTC Vive. So at that time, I'm very curious about what's very, very fun. But there is a HDMI cable, I mean, underneath your head. So it's kind of very strange. Can I get it, because I'm an engineer, right? I think, can I get rid of that HDMI cable? Yeah, I did a study and just found out it's so tough, because basically it's a 4K resolution and 90 frames per second. That's a lot of data through the wireless. But I did a study. I think the latency is a very important issue, even you're using the cable, right? So it has to be, even that cable is very expensive one, because it's longer. The latency from there, so when you move your head and there's a sensor will send the signal to the graphic card, and the graphic card will render a video and send to the goggle, right? This is a kind of a loop. So if the overall latency is over 30 milliseconds, so people will feel dizzy. So if the move ahead, the picture didn't respond. Yeah, the people will feel dizzy. So that's my initial target, to do the low latency video link. Is not for APV. Right. So I was doing that. But so when I doing that design, that I talked to a lot of my advisor and classmates. So because all coworkers, all of them are video communication, I say I want to do a very low latency, 30 milliseconds. Everybody saying it's not possible. That's why HTC, even the Oculus, the Facebook, they cannot have such a solution, the wireless solution. So especially the solution is on the 6 gigahertz. So right now they have for the UWB, right? They can have a very wide frequency range. They can do that, but on the sub 6 giga, they cannot do that. So everybody say no. But I think probably I need to try it very differently. So that's why I say it's a GASSC. It's kind of the technology I'm going to use, because everybody knows you want to communication the video, right? You first do the compression, then you do the ofdm stuff. This is written in the textbook. Everybody knows what to do. So as of today, everybody knows what kind of the compression, what's the compression ratio you are having. So what's the ofdm? What's your data rate? What's your bandwidth? People always ask me this kind of question. So for HDZero is very different. They don't have those kind of parameters. So you ask me those parameters because you think I'm doing the compression, those kind of things, but I didn't. If I did that, you cannot have the low fixed latency.
Fantastic. Well, I think that brings us on really nicely to just an overview of the HDZero system. So can you talk us through as a sort of summary of exactly how the HDZero system works from sort of the camera through the VTX to the VRX and then finally to the goggles, just as a summary, and then we'll go into each section in turn.
Oh, okay. So the video from the camera is through the Mipi and to my chip, and we have to go to the Mipi to get the YUV data. Then we do the video process. I will not say compression, but it does remove the redundancy of the video, get the video data smaller, then pass this data to the baseband, and the baseband come out the signal to the that everybody is the same to the radio frequency modulator, then out to the PA. Yeah, it's kind of this flow.
Perfect. And then when that signal arrives in the HDZero goggles in the VRX, is it a similar process in reverse?
It's the reverse direction, right? Yeah, we get the RF signal, we do demodulate the RF signal, then pass the baseband, and the baseband we will get the data, and pass the data to the video processing again, then output the video. Yeah, it's just
Perfect.
a reverse. Yeah.
Thank you. So I think that's a fantastic summary. So let's jump into, I guess, the camera side of things. And I was doing a bit of research on the different cameras, and my understanding is that most analog CMOS cameras and the DJI CMOS cameras all use a rolling shutter. And I was interested to see that HDZero, the Cam GS, used a global shutter. Could you talk to us a bit about the difference between rolling and global shutter, whether one is better than the other, or what your thoughts are on that?
Right. Global shutter definitely is a more advanced technology, and it's very powerful when you like it. As of today, people scanning the QR code, right, with a camera. Even you fast moving, so your software will probably have the problem. But with the global shutter, you definitely will make your life easier, right? And for the LPV, when I first jumped into LPV, I think global shutter is the best. Then I was, at that time, I was doing the fight frost. I'm using the global shuttle. But the global shuttle, we will introduce a one frame latency. That's one of the things. So the rolling shutter, the light gets one line, and the one line out, right? You get the other line, right? Maybe a few lines, right? But it's not a frame, right? So the global shuttle, you get one whole frame. So you get out, then you explore the other frame. So basically it's one frame latency on the global shuttle. But because the APV is a high motion, the global shuttle will help. So it has benefit and it is advantage and disadvantage.
Yeah. So for sort of the lowest latency, a rolling shutter might give you slightly lower latency, but the global shutter is going to give you better capture of the motion.
That's right. It's called blurry, right? So the global shutter will give you very clear image without blurry. But the rolling shutter, definitely, if you see the props, you always see
they get
like
bent. They bend.
That's right. Yeah. Right. But the global shutter will remove that. Yeah.
Perfect. And so, is that the sort of direction that you're thinking that your technology will go in the future, using more global shutter cameras, or do you think you'll support both types, or what do you see in the future?
I think I will support both types, and the price wise, people are very sensitive to the price. Global shuttle is much more expensive than rolling shutter.
Yeah, fantastic.
Right. The other one is the frame rate. So for example, DJI use 120 frame rate per second, and that's another higher barrier to produce the qualified high frame rate camera sensors. Yeah, not so many companies can do that. It's kind of expensive one.
And speaking about frame rate, obviously, you know, there's the cost associated with the high frame rate. Do you think that your technology, you would apply your technology to different frame rates in the future? Or do you think, you know, 60 frames per second? What do you see in the future?
Okay, so when I first designed this, I'm thinking about the cost. So I think my system cannot use a high-end, like a high expensive CMOS sensor. We have to use the commodity, right? So that's my plan. But my system does benefit if we have the higher frame rate, because the people are looking for higher frame rate, right? Starting from the TV. Before was 60 inch, now it's 60p, right? 120p. Now it's 240p. So yeah.
So as you say, it's really a cost thing. The system can support higher frame rates, but we all need to be aware that those sensors are much more expensive, and that's going to be a cost that will be more than a 60 frames per second sensor.
Right, the cost is higher, and the availability is kind of a problem too.
Right. So they're not always available, and they go out of stock quite quickly and things like that.
Right.
Yeah. Okay. Fantastic. So that data that you capture from the sensor, there's some image processing that goes on in the camera, I guess, with a specific image processing chip. Is that right?
Right.
And do you use a particularly special type of chip, or do you use similar image processing to other FPV cameras in your system?
Oh, actually, in my system, I know something about the image signal processing. Most people, I mean, IPV, they do, but it's kind of scientific. I'm not an expert there, and the Roncam, even Fox, they're using the asic to do this job. We call ISP, right? Right. The Sony, they have their own ISP. I think DJI is very good at the ISP too. They right in earlier time, probably they don't have the ISP chip, but they are good at tuning it, right, to make it look very nice. But right now they are too big. I think they might have their own ISP for all the cameras. But definitely DJI is very, very strong to make the picture looks nice. Definitely, that's for sure. I think probably, I'm not sure, maybe, yeah, it's very strong.
But as you say, there are several suppliers. There are a few different suppliers of these image signal processing chips. So it comes down to the camera manufacturers, I guess, to find the best available chip and to tune it correctly. Is that right?
Yes.
Perfect. So we'd have to, I guess, look into whether DJI do actually have any proprietary ASIC for image signal processing. I'll put something down in the video description if I can find any evidence of that later. So now you've got the processed image that's transported over a Mipi link, which is a digital video link. And at this stage, the video is uncompressed. Is that right?
That's right.
It's kind of the raw data. So can you tell me a little bit about the Mipi link that you use? Any particular specifications that you feel you can share about that?
Okay, before I jump that, I want to make a little correction. It's not called raw data. When we say the raw data, it's kind of the CMOS sensor give to ISP. This is called raw data. It's called it's called bear format. It's RGGR. There's that's called raw data, right?
Yes. Sorry.
So the the video data after the ISP is called YUV data. The YUV data is visible. So it's a YUV data over the Mipi link.
Yes.
The Mipi link, there is a protocol, is called Mipi CSI2, right? So the Mipi consists of two things. One is a PHY, the other one is the controller. The PHY basically is like a track, right? But the controller is what's the payload on the track, right? These are two things. So we have a Mipi TX on the camera side, and we have a Mipi IX on our receiver side. Yeah. So in our video transmitter, there is a Toshiba chip. That's the Mipi IX. Yeah.
Right. And do you use several lanes in your Mipi link to get the data rate high enough?
Oh, that's right. Mipi is a very, very good is a standard, right? Because we are only 720p, so we actually can use two links or four links or four lanes. Sorry,
4 lanes.
4 lanes or 2 lanes. That's fine. It's because our data rate is very small, right? Compared to 4K. Yeah.
Sure, absolutely.
Yeah.
And I guess you use for your system, you can use 2 or 4 lanes. Is that right? Or
right, we can use both.
Right.
Right.
So
that's why I say Mipi has lots of parameters. So I need to I'm 4 lanes or 2 lanes, right? And what's the color space? What kind of the YUV data there? So that's why we needed a handshake IC for that.
Yeah, absolutely. Well, that's really great because if you support up to 4 Mipi lanes, that potentially means that the data rates could theoretically go higher in the future, I guess, with either higher frame rate, 120 frames per second, or even higher resolution. Is that true?
Yeah, you are very smart, and this is a very good question. The reason we choose 4 lanes means, the data rate is half of 2 lanes, right? So the lower the data rate, meaning the Mipi cable can be longer.
Right.
Right. So this is the reason we choose 4 lanes. Right. One of the reasons. And the other reason, for the later on, we can support a higher resolution. Yeah.
Yeah. Oh, fantastic. So that's something that I didn't realize, that you could run the Mipi lanes at different rates to achieve a different to allow you to use longer wires and achieve better signal to noise ratio, I guess, on the link itself.
Yes. Right.
Okay, awesome. So we've got the YUV data that's been processed in the camera. It's over the Mipi link, and then it gets to your VRX, so your VTX module, and through the Toshiba chip there. What's the next stage? Okay, so here is kind of very different. It's very different. I will not. Right, I will try to explain as much as I can. Okay, basically, the other solution like Wi-Fi or DJI, they will compress the video. The compressed video will be, the video stream is not kind of stream, it's kind of a package, right? Each package has a header, has a lens, has a payload, those kind of thing, right? And those things will pass through the baseband demodulator. So here is a problem. So each bit is very important for that stream. If you mess up 1 bit, maybe your whole package is gone. For example, you have 1 bit wrong on your lane, so the whole package will be wrong, right? Will be very wrong. So my approach is very different. The difference is I think about the video. So the video, basically each pixel is easy to understand, is RGB, right? So RGB AA is 24 bits. So I can tell you, even you have only the MSB, like the R7, G7, B7. So you will get the image. So which means you only transmit 3 bits instead of 21 bits, 24 bits. So you will basically
get the basic image.
And you
That's
sort of
the
get
whole
most
idea.
of the data.
Right.
And do you?
Sorry.
Sorry.
What I want to say is, so if you compress the data, each bit is very important. So if you do the video, if you analyze the video data actually, some of them important, some of them is not. It's not equally important. But I can say that, right? Yeah. So I need this. I utilize this feature to design my file. So, which means the file meaning to design the file. So for the very important data, I will make sure I have more protection for that.
I see.
Right. So for the less important data, I don't have any protection for that. So if my bandwidth is not enough, I just get rid of the less important data.
Right. That makes sense.
Right. So this is a very different with the other solution, because I think not every bit is equally important.
And you were saying you're talking about YUV data for people who maybe aren't familiar with YUV. The Y is the luminance, isn't it, of the pixel?
That's right. Yeah.
And then U and V are sort of the color data bits. So I guess you would view the Y data as being more important, let's say, than the U or V data, because the brightness of the pixel is what our eye is really sensitive to more than just the color, right?
Exactly. And also the Y, the bandwidth for Y is much longer. So because but the UV is kind of only limited in low frequency. So that's why it's easy to transmit.
Yeah. Okay. Fantastic. So it's sort of, in some ways, you're taking the same approach that you're taking the same approach to the importance of the different parts of the image as in an analog video, where again, certain, for analog video, the Y data is prioritized and sort of sent with the maximum possible signal to noise, and the color data is sort of the first to get lost in a sense. So I guess you're taking a similar approach, but with a digital signal rather than with the analog video signal. So that's really, really interesting. So once you've got that stream of data, can you talk through how you would process a frame of video? If you receive a frame from the Mipi link, does the frame arrive all at once?
Oh yeah, that's a very, very good question. So we were talking about the video data itself. It's kind of the still image, but video actually they have timing. You are talking about the timing, right? Yeah, this is a very important topic. So we are not only transferring the video, the pixels, we need to transfer the video timing. Right. Otherwise, okay, you lost one video, right? You lost one frame. So the other side doesn't know. So you will have the freeze video frame right over there. So that's a problem. So, but it is very difficult to transfer even a single bit over air if the signal noise ratio is pretty low. So you need to have some way to get your video timing to the VRX side. This is this question is, I won't say the most important thing of this system, but it's very important. I think we solve it pretty well, because our frame rate is kind of, even there's a snow noise, and but the frame rate is pretty constant. It's because of that. But thank you for asking this question. Yeah, this is very important. It's not only the YUV data and also the timing data.
To make sure that the frames are being displayed at the right time on the other end. Otherwise, you could potentially get strange things happening where over time, the latency of the link is changing at the other end because of missed frames or lost data. Yeah.
Yeah, that's it. Thank you.
Yeah, very, very interesting. So you get your data from the Mipi link, and you say, does that data across the Mipi link arrive sort of line by line as it arrives, or do you get whole frames at a time? How do you transfer the data for one frame?
Right. We just get a few lines, and then we start trying, because we want basically. So if you check our VTX, there's no DDR in our VTX, which means even we want the video data is huge, the YV data is huge, so you cannot save in the ASIC inside my chip. My chip don't have memory inside.
Right.
So in that case, meaning we don't have any buffer for the frame, so we can frame only a few lines. So you're just processing that video data the moment it arrives and transmitting it. There's no delay or any waiting, because there's nowhere to wait, if you like. There's no space to wait. That's the design purpose. Right? Yeah, the low latency, you have buffer everywhere, meaning it's not kind of low latency.
Yeah, if you have a buffer, it's not going to be low latency because you've got data waiting around. That's okay, right. Yeah, that's really cool. So yeah, it's transmitted over as you said, an OFDM link. Now, when we spoke before, you described your OFDM link, and it's quite different from like a typical Wi-Fi link. Can you talk about how it sort of differs from traditional Wi-Fi?
This, I think you are expert, but yeah, this is a very good question. So when we talk about OFDM normally you need to have a C, is called COFDM, is called coded OFDM. So mine I call it the AOFDM. So I invented it's COFDM, meaning the data comes in, you code it. It's called channel coding.
Yes.
It's channel coding. Yeah, it's called channel coding. You get a 1 bit in. For example, there is a convolutional coding. The 1 bit can become 2 bits, or 7 bits become 8 bits. It depends on the ECC, the capability, the correction, those kind of things, right? So when you say you have a 50 megabits per second in, but output is over 100. Right. If the 1 bit become 2, that's already 100, right? Yeah. And also there's another like Reed Solomon encoding. That's 188 bytes become 27 bytes. That's another overhead, right? Yeah. We add those kind of overhead before we transmit, just for ECC. Just like some error happening, we can correct it.
Right.
But we don't have it. We don't have those kind of things.
Right.
So this kind of thing, like the convolutional coding, they have the buffer inside. We need to get rid of that buffer. DJI Open HD Wi-Fi is everybody is called COFDM. I never call mine COFDM. I call myself OFDM or AFDM, AOFDM. Yeah. So mine is not coded. Yeah, I'm not coded as a traditional way, but as I said, because my bit stream comes in, each bit stream have different priority. So I need to do different mapping for each kind of stream. So
right.
Yeah. So that's the trick part of my design. So we have many priority data comes in with different priorities. So how you map into the different constellation, that's one of my tricky job.
Right. Yeah. So you actually treat data that comes in differently depending on whether you view it as high priority or low priority in terms of how you, is that in terms of how you encode it, you know, what modulation you use on the baseband, or or which channels you put it on? How do you treat the data differently?
Oh yeah. So first there is a constellation mapping. So you need to look about that. The constellation mapping. Then, for example, I'm not doing anything about the correction. I do for the priority one, especially the timing one. I need to do the protection. I need to do the channel coding. Probably is not 1 bit become too big. Probably is 1 bit become much more than 2. So because as I said, the timing is very important. I can lose the whole frame data, but I cannot lose the timing.
Yes.
So that's very important one. So yeah.
Right.
It's kind of
So that's how you do it. You sort of, as you say, you convolve the important data to protect it and make it easier to decode at the other end accurately. And then the less important data, you don't do so much of that sort of error correction convolution to sort of help. That makes a lot of sense. I think that will be really clear to people. So can you sort of say what is the rough kind of data rate that you send over the ofdm link in a normal situation? So first of all, the data rate has to be variable because it depends on the air SNR. Yeah, it has to be different. Otherwise, the fixed data rate is kind of suicide to me. Yeah.
So that's one of my design spec. So in average, I think I don't remember. It's close to 100, 97 or something. Yeah.
Wow. So that's.
But sometimes it's over 100. The average should be 97 or something. Yeah.
Right. So I think that will sort of surprise and I think impress people that actually, although you've only got you're using a narrower band, 27 megahertz versus I think the 40 or something that DJI use, the way you do your modulation and the way you prioritize the different data in the link allows you actually to move more data through that channel than any of the other systems. I think certainly more than DJI are able to anyway. So I think that's it's quite impressive in terms of the amount of data.
Right, here is kind of little. So we are talking about actually the different thing. So when DJI says 50 megabits per second is called usable bit rate.
Usable.
Useful, right? But I'm talking about the 97. Actually, is a 5 bit rate.
Right, that's the actual link. Right. That's the link rate basically.
Right. So when DJI says it's called 50 megabits per second, I think is on the air the link is over 100.
Right.
But because it has all the correction it has all the data have the error correction, right? I mean the redundant speed. But for my stuff, it's not. Some of them have a lot, some of them hasn't. So I have 100, but my useful bits definitely is changing, right? Right. Yeah.
So
we're talking about the different things. Yeah.
Yes. No, that makes a lot of sense. So yeah, you've got about 100 megabits per second of the link rate, and how much of that roughly would you think is going to be useful data, and how much would be that error correction?
Right. It really depends on the SNR. In the low SNR, when I only transferring the timing, let's say the worst scenario, I using 1 frame time frame, what should I say? 1 frame during the time of 1 frame, let's say 1/60 seconds. I transfer only 1 bit.
Right.
You think how much bit how much protection I have put it on. So I put it a lot, right? So during like it should be 8 milliseconds. I only transfer only 1 bit just for the timing, right? Yeah.
Right.
That's a lot. Yeah. But if the signal is very good, So I transfer all the details. In the other case, so my 97, maybe we have a 80 megabits per second. It's all useful, right? It really depends on the current, the channel condition. If the channel condition is bad, maybe all the useful data rate will be very small. But if the SNI is good, the useful data rate is close to the 5 data rate.
Right, that makes a lot of sense. So yes, your link rate will always be the same, but as you say, the useful data varies to accommodate the different channel condition. So,
exactly. Yeah. Thank you.
Yeah, perfect. So you've transmitted it over the air, and it arrives at the goggles. And as you say, some of that data is going to arrive undamaged, uncorrupted, and some of that data is going to have been subject to some interference. How do you manage data that might have been damaged during transmission when it arrives at the goggles?
Yeah, first of all, we have a kind of the indicator is called flag, right? So how this bit, how this block, I would say block, how this block, how the data, the status over there. So if you found this data is it's not the white or black, meaning, so this is block data, maybe only some of them get damaged, right? We will identify that. So if it's damaged, it's totally damaged, we will consider using its neighborhood to regenerate it. Right. But most of the case, we get only half wrong, half right. So we need to make the decision to do that. Yeah.
Right. So you've got a sort of error correction code when you're in your ASIC that can take a block that's only been slightly damaged and sort of repair it in some way. Right.
Because so we have some kind of error correction, right? If in the minor damage, I can fix it.
And how about for a block that's been significantly damaged, where it's mostly missing?
That's right. I need to use its neighborhood pixels because I transfer the raw data, not the raw data, the image data, right?
The image data.
So the image data. So if the image is gone, I can look at its neighborhood, right? Its neighborhood or blue. I would think probably I'm blue too, right?
Right. Yes. So you're using effectively a sort of intra-frame prediction technique to look around the pixel and figure out what it should have been.
That's right. That's the right terminology.
I've been practicing my terminology. Great. So I think that sort of explains things. And then when you're displaying that data into the goggles, do you display it all at once in the way that DJI does, or do you display line by line as the data comes through the system?
Right. When I design this system, the latency is one thing. So when I get only one line of data, a small piece of the data, I will start transmitting. And here, once I get the small piece of data to display, I will throw it out.
Right.
Once again, I'm using the same chip on the transmit and receiver side, which means I don't have the memory on this side either.
Right. So
actually, I don't have buffer to save the data.
Right. So the data is going straight out of your chip into the HDMI link, or directly, into the HDMI link from the VRX.
Right. HDMI link is a final stage. Right. So for me, the output is called BT1120. This is kind of standard. The BT1120 can go to HDMI TX chip. Right. There's a chip, converts BT1120 to HDMI signal, or can convert to SDI, whatever thing. Yeah. The chip itself is come out as BT1120 signal.
Right. And then that HDMI chip, does that have any data storage in it, any buffer, or does it convert and transmit down the HDMI cable sort of instantly?
I'm not an expert there, but I don't think they have any buffer. Maybe line buffer, but I don't think they have buffers because the HDMI thing is kind of like the Mipi thing.
Yeah. Right. So it would be, so you don't think there wouldn't be like a whole frame buffer to just store everything. It's likely to just send it to the screen as you send it the data.
Right. That's on the transmitter side. On the receiver side, it may be a little bit different. So this is a HDMI transmitter, right? There is a HDMI receiver.
Right.
On the HDMI receiver, it need a little bit of time to train its circuit to trace the incoming video, incoming clock or data, those kind of things, then convert into the BT1120 to display.
Right. So it's going to be up to the way that the goggle is implemented in a way into how it's going to treat that data that it receives, whether it's going to display it immediately or whether it's going to buffer a frame and then display a frame. So that's something that I guess is important.
That one I am not very sure about that. Actually, each display is very different. Like OLED and our OSD. LCD is very different. Some of the LCD, they have a very strange chip. It's kind of a, most of the chip is like a square, right? Small square. It's kind of a, the display chip is very different, and some of the display chips do have the memory inside. Because you need to drive. But once again, I'm not an expert there. So what I can do is I get the data, I will transmit immediately. I get it, and once I receive it, I will transmit. Right.
So any latency that might be added by the goggles as a function of how it handles incoming HDMI data is separate to your system, and that's going to be down to the way the goggle is made.
Right. And even the goggle maker probably that doesn't know. Nobody knows the inside. Only when we're talking about the display, let's say OLED, right? The OLED, so they have some signal. We pass the data to that, meaning we only pass the data to the interface, right? How it display the real image on the panel, there's a chip to do that. How that chip works, we don't know, right?
Yeah, I think this is going to be interesting because in the next few days and weeks, I'm going to be doing some high-speed video of the screen inside the goggles, and I've already done some testing, and I've looked at an analog goggle, the Onway Commander, and I've looked at the DJI goggle, and with the analog goggle, you can see it drawing the image line by line. At the same rate that the analog scanning is happening. So it takes a whole 17 milliseconds to draw a whole field as it scans line by line. But the DJI system, the screen just instantly updates the whole screen in less than a millisecond. So it's it's not line by line. It probably is line by line, but it's buffering a whole frame and then displaying a whole frame.
Right.
That's
my expectation. That's my expectation. Right.
Yeah. So your expectation is that most HDMI goggles will work similarly. That they'll buffer a whole frame, and then when they've got that whole frame, they'll display it all at once.
No, I'm thinking the DJI, right? The DJI, they're doing not DJI. I mean, the other solutions, they was like they have the data, they do the compression, right? Decompression. They have the whole frame at once. That's why they display it, right? Right. But for us, like analog, we only get a few lines. That's what we can do.
Right. So actually, that could be a benefit because if you've got that few lines and you display those few lines, if the object that you're looking for happens to be in those lines, then you see it sooner.
Yeah, but when you test it, probably the photo died, so it's kind of the the curve maybe take time to rise up, right? Because the DJI the pump up immediately, so it immediately indicated the sun. I mean, when I read the report from Ryan and Jeff about their testing method, I think they do a very good job. That's my expectation.
So something that I'm working on and I'm going to be doing is a similar type of test, but rather than a photodiode, I'm going to be using a high-speed video camera. So you'll be able to see the screen, and you'll be able to see how the screen is updating. And it's similar to the photodiode, but it's like having, you know, lots of photodiodes all over the screen, I guess.
Right. There's a photodiode. Theoretically, there's no problem. But the thing is how to set the threshold is kind of the problem, right? As I said, DJI, they from 0 to 100 instantly, right?
Yeah.
But for the analog, we gradually. So how to set the threshold is kind of very tricky. If you set the same threshold, so definitely
it could be different.
Yeah. Right. Yeah.
I hope that when I do the high-speed video, it will be clearer to see what's going on, because you'll actually be able to see the screen as if you were looking at it and actually see how it's updating in real time as the image comes in. So that hopefully should clear a bit of that up.
First of all, I think the latency test actually is very difficult. It's very difficult. It needs equipment and needs technology. And it needs knowledge too.
Yeah. Well, what I'll do after this call, Carl, is I'll send you over the videos that I've prepared so far on analog and DJI with my high-speed camera, and we'll see what you think of them. And maybe you can make some comments, and I'll put them down in the video description. What you think? Right.
I'm very interested. I really like this kind of thing. I like challenge. Yeah.
Absolutely. So I think we've kind of talked about the latency side of things, and I think that's going to be something that obviously we're going to get more information about when I do my testing and as other people kind of refine their testing methods. And it's great that you're engaging with all the people who are doing the testing. I think that's something that, you know, we don't see DJI doing. Like they're not engaging with the community in the way that you are. So I think that's really great.
Right. Everybody says that, but I'm small, right? I have nothing to do. DJI is big, so.
Yeah. Well, you know, I think it's wonderful that you take the time. As we sort of come to, I guess, the sort of the end of our time here, I wanted to ask you a few questions about, you know, the future technology that you're working on with the system, and how you see HDZero progressing into the future. What types of new products you're thinking about. Obviously, you've got a relationship with Fat Shark. Do you expect to build relationships with other companies as well? Do you want to talk a little bit about what you see for the future for the technology?
Oh, okay. For the current technology, so we are weak in the penetration and the range. So we definitely need to a higher watt VTX for that. Right. And also the current camera, because we don't make a camera, right? We put a request to Runcam or for folks, ask them to make camera. But it seems like we need to co-work with them more. Because, for example, if we can reduce our frame rate from 720p 60 to 720p 30, that's our bandwidth will reduce from 27 to 13, which we have a much better range and a much better penetration. If you think about this kind of range and this range passing through the air, this range is much easier, right? So this is the kind of thing. So the camera, before a lot of people say, oh, the HDZero is analog plus. It's like a 360, right? It does look like, but until we have the HDZero come out and say, oh, okay, this system has some potential.
Mm.
They were right, but actually they are wrong. Then the penetration and the range, if we can manipulate the camera setting into 720p 30, if we think something is wrong, so definitely we can improve the range and the penetration without changing anything.
Right. So you're looking to actually integrate more with the camera, and actually, if you're going behind a wall or something and you suddenly get very low signal, you could actually switch the frame rate and so okay, it's a lower frame rate, but you're still getting that image through. You're still seeing, you're still able to fly.
That's right. Yeah. That's really one of the other, our chip actually supports 1080p 30. So yeah, I know it's a kind of lower priority because the goggle itself, no goggle supports 1080p yet, right? But this is the kind of thing we can do.
Do you ever think I know you've got your own camera now, the HDZero camera. I think it's made by RunCam, is that right?
Yes.
So do you think you'll continue to do your own cameras in the future, or are you hoping that partners are going to take over most of that?
Actually, I want to get rid of the camera and the VTX and the VRX, everything. I want to sell chip.
Right. So
that's my ultimate goal. I'm an IC design company. Daniel English, he has a video. He asked me about that. I told him about the reach wave. I want to be a reach wave. Nobody knows me, but I'm doing the analog video transmitter receiver thing, right? Yeah, nobody knows reach wave, but actually they're 100% market share.
Yeah, I see.
For the analog.
Analog, but that could be really great. So it wouldn't just be HDZero, and it wouldn't just be Sharkbyte, but potentially everyone who currently makes analog VTXs could be making HDZero VTXs in the future.
Right. Actually, everyone come to me who want the chip or the module. I think I welcome them. Anytime, contact me if they need the chip, need the sample, need the reference design. No problem, I'll give them.
Fantastic. Well, I think then we have to throw the gauntlet out to all of those manufacturers who currently make analog VTX. We want you to go and make Sharkbyte digital VTXs as well. We want to see what those products look like and get some more competition in the market and get some more products in people's hands. I think that would be really cool.
Yeah, that's the thing, right? We are the new technology. We are a small company, and we have a huge competitor. So nobody wants to get in. There's nobody. I mean, making the HDZero products, not because we are not open, because they don't want to come in. Right? We have to prove ourselves. Okay, this HDZero is okay.
Yeah.
Then they will jump in. Yeah. So people misunderstand that.
That's right. Well, I think it's wonderful to hear, and obviously, I think everyone is going to be very pleased to understand that in the future we could see, people like TBS and Rush and AKK and all these other companies that currently make analog VTXs and make really good ones, could also turn their hand to making Sharkbyte VTXs, and potentially that would be a great partnership, a great combination.
I think I made a lot of mistakes. So for example, I still think I'm a very good ASIC designer and algorithm designer too. Yeah, right. But I'm not a qualified system designer. So we made a lot of mistake when we make the VTX. The first thing, so when people, so that's right, kind of, we have the tough situation right now is because of that. So for example, when the first 200 units, so we shipped, it has some problems. Some of them, some guy only test on the bench is dead. So actually, yeah, it's our mistake. We don't have much experience on that, and we made mistakes. Actually, it's not our expertise. It's not. Our expertise is the algorithm under the chip. We want to do that, right? But with the chip, with the huge competitor, those analog companies, they won't jump in. What can I do?
Yeah, what can you do? And I think that what you've done is, you're showing a proof of concept, a proof of principle, an MVP product, as it were, to demonstrate that the system really is, has that potential to be great, and that really, we should be seeing people who currently make analog VTXs thinking seriously, because in a few years' time, no one will be flying. No one is likely to be flying analog anymore. I'm a firm believer that digital technologies, DJI, HDZero, I know we've got OpenHD as well. These technologies in a few years' time are going to be the dominant ones, right?
Oh yeah. So the digital, let's say we have 8 channels. 8 channels. I mean, I don't know why they say to the 25 milliwatts for the racing, right? Because it will not affect each other. But for our system, even you set at the 200 milliwatts, you have 8 players play together, no problem. You don't need to say 25, right? Because our spectrum is like the door, right?
Yes.
The analog is like this.
Yeah, it goes out.
That's right. Yeah, it will invade the neighbors.
Yeah. Well,
right, but the digital is great. It's no problem to do that. Yeah.
I think that's also something that's really great to hear, is that we might be racing on 200 milliwatts or 500 milliwatts or even more in the future if everyone's running digital systems like HDZero, and that means that we could have even more exciting racing through courses where there's more obstacles, more things that interfere with RF, because we can actually fly at higher powers for racing. So I'm excited to see how that will affect like the race course design and stuff in future, when you can have pilots flying through buildings and through trees and not worry about them losing signal.
Oh yeah, and also the digital, they occupy the less frequency band. So right now the R1 to R8 actually is only, I'm not sure, it's only 2 or 3 or 4 of them are legal. Are legal. The other is not.
It certainly depends on the country, doesn't it? Depends on where you're flying.
Yeah, that's true. Yeah. Yeah. So what I want to say, that digital, they occupy, let's say we are only using 27, right? But from R1 to R2 is the span is 30 something, right? 36 or something.
Yeah, it's wider than 27. Yeah.
It's wider, right? It's wider than 27. I mean, we can squeeze more channels.
Yeah, and get more pilots in the air.
Yeah.
Ah, fantastic. Well, I come to the end of my questions. I think Carl, you've been wonderful, and thank you so much for answering. Is there anything that you want to ask me or ask anyone who might be watching this and about to type a comment? Do you want to ask anything of anyone?
Okay, I want to say something.
Sure.
So I know the HDZero right now is still immature to somebody. I think that's true, but we are improving. We are listening the requirement. We have some very good helpers help me understand the requirement. I'm yeah, that's my last thing before my retirement. I need to do it right. I want to do something like I was doing the video surveillance thing. So it's analog and NTSC from 2005 to 2014. I'm converting the analog to digital. Now I'm doing the same thing. I want to convert the analog to digital for the LPV domain. For the
right.
Yeah, that's my goal. That's maybe my last job to do that. Yeah.
Fantastic.
I want to make money, but if it doesn't make money, I'm okay. Yeah. I have a dream to do that.
Fantastic. Well, I think that your passion for it really comes across. And I think that will really connect with people. It's about it's kind of why we all do it, right? We all do this because at the end of the day we want to try and make the FPV hobby better for pilots, and that's the goal.
That's right. I love the LPVs, those people, those pilots. I mean, not all of them, definitely, but most of them, they are warm-hearted, glad to help. When you ask them, they're very glad to help. I will not name anyone, right? But they are in my heart. They support me. So even I made mistakes after mistakes, yeah, but they forgive me and give me a chance. Yeah.
Yeah. Well, I think we're all, well, I certainly am 100% behind what you're trying to do. And I'm very excited to be making all this content about your system. And, I think hopefully people who watch this will understand, what you're trying to do, why you're trying to do it, and why it should make things better for pilots in the future. And that we can all do what we can to support you in trying to make that dream a reality, which I think is really great.
Yeah, that's very cool. I want to make the FPV, this hobby, better. That's for sure, right? Yeah. So the HDZero doesn't hurt, it doesn't exclude anyone, right? We want to convert analog to digital. Digital have many beauties, so we need to convert, right? But for example, as of today, I lost a lot of money to do that, but I'm never regret. I think the LPV pilots, I love them. Really, I love them. Yeah, they help him a lot. They help him a lot. Yeah. Yeah.
Oh well, that's fantastic. I think that's all we probably need to say today. What do you think, Carl? Is there anything else you want to say? I think that's a lovely note to end on.
Thank you, Chris. Give me this chance. Thanks.
No problem. It's always lovely to speak with you, Carl. And I wish you all the very best. Thank you for taking this time. And I hope everyone who's watching this video also enjoyed it. And we'll leave any questions they have down in the comments. I'll certainly try and reply to as many as I can. And we'll talk about this a bit more in the future.
Yeah, thank you.
Thanks, Carl. All the best. Take care. Bye-bye.